I know that working with shorts can be a little frustrating to you guys, so I'm going to do a full-length video on the carbon microphone replacement circuit, specifically the T-17 carbon microphone used on many military transmitters in World War II. Both airborne, Navy, and ground-type radios use this microphone. So we'll go through my carbon mic replacement solid-state circuit. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. This is the TCS Navy transmitter receiver setup, sometimes called the TCS Twins. You might recognize these radios from Mick Hale's Navy, a popular show in the 60s. These were put on as the main transmitter receiver setup in many small boats and transports, including the PT boats, and as a backup transmitter in probably everything that floats in the Navy in World War II. So the carbon mic replacement would be a good candidate for this particular radio. So anyway, we'll go over the circuit. It basically uses a TIP 120 Darlington transistor. The Darlington transistor is a couple of transistors that are hooked up in cascade, so they have increased HFE, or current gain. What's so special about current gain? Well, what is a carbon microphone? A carbon microphone basically is a resistor. It's a resistor that changes as you talk into it. So with a carbon mic, the impedance of the microphone changes as you speak. And it's that change in resistance. Of course, we have a voltage involved and a current going through a resistor. So when you put a current through a resistor, what happens? You produce a voltage. That's how the carbon microphone works. So as you talk, the resistance changes, and of course the voltage is going to change. It's just Ohm's law. So with the solid state replacement, you want to be able to control a resistor, basically. How do you control a resistor? What's the correct device to act like a variable resistor when you're putting a variable voltage on the input? The voltage in this case is coming from an electret element. Well, it's called the transistor. A transistor is a perfect device to make voltage change a resistance, specifically the resistance of the transistor's conduction in the linear region. So that's what we're doing with our carbon mic replacement. We're taking a simple electret element, giving it a couple of volts of bias, and then putting that into a transistor to convert the voltage changes as we speak into current changes, and that's how we're modulating the transmitter. That current change is going through a transformer that's usually inside the transmitter, and that current change in the transformer in the transmitter is a form of magnification of the voltage going right to the grid of the modulator tubes. There might be one stage of voltage amplification inside the transmitter. Sometimes there's not. In the TCS, we actually have a step-up transformer, and it's a push-pull grid-type transformer that drives the grids of the 1625 modulators directly. So that's pretty cool. We're going from a microphone into a transformer directly into the grids of the modulators. 1, 2, 3, 4, 5. Hello, test. Hello, test. This guy puts out about 10 watts in the AM mode. Let's look at how the carbon mic replacement actually works. First, the carbon microphone. Let's investigate the carbon microphone and then move into the replacement circuit.
So very quickly, a carbon microphone is a device that changes sound pressure waves into a way to modulate or vary an electrical current. This fluctuation in current creates an alternating AC wave that perfectly mirrors the original sound wave. Of course, you need a DC power source and a resistance to transform this current into a voltage. Normally, the load is a set of headphones or a step-up transformer that feeds the grid of the modulator tubes. Basically, a carbon microphone consists of a small chamber containing loose carbon granules. This is called the button. External direct current, DC, from a battery is applied, causes electricity to flow through the carbon granules. So when you speak, sound waves hit the diaphragm, making it vibrate. These vibrations physically push the carbon granules together or pull them apart. When the granules are compressed closer together, the electrical resistance goes down. It allows more current to pass. And when they loosen, the resistance, of course, increases and less current flows. This produces a shaped AC voltage that basically mirrors the speech amplitude and the frequency components of your voice. Higher produced voltage is related to higher sound pressure. Understanding how the human voice is asymmetrical and you want more talk power, the concept of audio phase of speech becomes useful in your transmitter to produce the so-called desired upward modulation. The voltages produced with close talking a carbon microphone are pretty big, perhaps as large as 1 volt peak to peak. This level is very high, but it's not high enough to actually swing or drive the grids of a modulator stage. So either an amplifier or a transformer, or both, are required to produce the several tens of volts required to drive a typical Class B push-pull modulator. In the case of the Navy TCS transmitter, the DC is stolen from the cathode voltage drop of the actual modulator tubes. Pretty clever. The 1 volt peak-to-peak from the microphone is sent into a high step-up ratio microphone transformer. This is usually on the order of 1 to 50. So 1 volt peak-to-peak of audio could produce up to 50 volts peak-to-peak of audio for the grids of the very sensitive 1625 modulators. No speech amp is even required. Talk about simple. This is Collins, Designed for Reliability, Lesson 1. Simply use fewer parts. The older General Electric BC-191 and 375 used in the B-17 bombers. These were operational before Pearl Harbor, by the way. They used ancient, already obsolete 211 triodes in the Class B modulators. These need more drive and more power than tetrodes, so they were forced to use a triode speech amplifier after the microphone step-up. But they also needed a side tone and modulated CW, so that triode stage did useful triple duty in that transmitter. So let's talk about the solid-state replacement circuit. The voltages presented to the carbon microphone are pretty modest, usually between 2.5 and 10 volts DC depending on the radio. It turns out that most electret elements work fine down to 1.5 volts, and they're optimized for 2 to 3 volts DC. The actual transducer in the electret is a condenser microphone with a permanent charge. The voltage supplied is simply on board for the buffering FET. This FET acts as a buffer and an amplifier for the very high impedance output of the condenser. The output of the electret microphone is between 1 and 10 millivolts peak to peak, with peaks, if you're really close talking and yelling, over 50 millivolts peak to peak. To bring this level up, we need an amplifier device which can drive a transformer load easily. A single transistor is a little bit shy on gain. Although it's overkill in all respects, I found that a Darlington power transistor provided all the gain required, and in an essentially bulletproof way. The TIP 120 Darlington is well protected, it has a voltage and current specification well above, and it has a body diode for reverse polarity protection. Note that positive ground radios work with an ordinary carbon microphone because a carbon microphone is just a resistor, right? No polarity. But with the solid-state replacement, you'd either have to flip the entire circuit or flip the element and use a complementary transistor, a PNP transistor, like the TIP 125. So how do most folks handle military transmitters? A lot of people force-feed audio into the military transmitter, blocking the DC that might be present. I really wanted to emulate the actual carbon microphone, utilizing the existing DC and audio input windings of the various transformers. The goal was not to be able to tell the difference between the carbon T17 and the T17 solid-state replacement. This meant attempting to emulate the T17's microphone military response with the electret microphone. The T17 is a typical single-button carbon microphone with a shaped response between about 400 and 2600 Hertz. There's some anti-noise characteristics designed in with that kind of a filter shape. compared to a dynamic microphone. The pre-emphasized response of the T17 produces something we call bulletproof audio. It basically restricts the lows and encourages the power response of the male voice for maximum intelligibility over the radio circuit. It also is low impedance. Basically, this microphone is designed to drive a 40 to 50 ohm load, and it's normally a transformer primary. Now let's consider our 99-cent Electret element. Its response is flat as a pancake, basically from DC to daylight. It actually likes a load of around 1 to 2 K. Most amplified D104s, for instance, are fairly high impedance, just like the Electret is. They just can't drive low Z loads like that transformer that's made for the carbon mic. But before we go on to our design, let's explore the Electret rabbit hole a little bit more. Let's say you don't want military response. You really want a high-fidelity microphone for your current broadcast quality software-defined radio. And you're looking at all kinds of fancy microphones. You could spend a lot of money on a new microphone. But our lowly 99-cent Electret, if treated with care, mounted properly and suspended properly, believe me, it can blow away almost any microphone technology. After all, it is in effect a condenser microphone. And we know that capacitor or condenser microphones are the flattest on Earth. They're as flat as you get. The curves show this. So here's some lost knowledge I dredged up for you. Back in the 80s and 90s, a local ham, KA1SI, now WA1QIX, you might have heard of him, he came up with a very effective desk microphone configuration using the Electret for testing his new PDM transmitters. So using an ordinary Electret element, he found that mounting can produce a very flat response. The mounting technique he used was called boundary layer. The principle of boundary layer is that of preventing reflected audio from the room from entering the aperture out of phase and thus coloring the audio. Using a flat sheet as a barrier with the Electret surface mounted on the rear with a countersunk pinhole, the reflective phase coloring is greatly reduced when set on the desk at the appropriate angle to the speaker, and if properly terminated into a 1 to 2 K low noise preamplifier, like for instance the virtual ground of a low noise op amp or a common base amplifier. The results will be a very flat response. The problem with such a reference microphone is that it hides nothing. I'm talking pure response, truth. Of course, the little Electret has serious limitations compared to a professional microphone. For instance, it can't handle high sound pressure levels, it has a little bit more noise than some microphones, and professional microphones are suited to specific applications, and these are engineered at high cost. Of course, outboard processing is required with any microphone, any high-end microphone that is. So that's a rabbit hole freebie in case you can't afford a fancy Neumann condenser mic quite yet. It's a nice weekend project for you from the Microwave One channel. So let's get down to the nitty-gritty of the design. The T17 carbon microphones typically measure between 200 and 250 ohms for resting resistance, when you're just testing them on the bench, but they can vary wildly from maybe 100 ohms to 1500 ohms depending on manufacturer, the age, the health of the microphone. Resistance changes, of course, when in use, like a variable resistor. Normally the fixed bias on the microphone, going through the transformer primary and whatever voltage they're sending to it, is between 20 and 80 milliamps, with higher bias generally giving more output on just about any kind of carbon microphone. So to the schematic. On the original schematic I included a 100, I can't remember if it's a 100 or 200 ohm potentiometer in the emitter of the device as a gain control. But typically this ended up at 0 ohms, pretty much full gain for most radios. So that emitter resistor, a 4.7 to a 6.8 K emitter resistor, that basically sets the gain. You may recall that we're acting like a variable resistor with the Darlington, and some bias is stolen for the electret through a 470 ohm resistor. A filter cap between 47 microfarads and whatever you can find, 220 microfarads. That electrolytic provides a steady DC bias for the electret. And usually the electret runs very nicely between 2 and 2.5 volts. The 2.2K drain resistor is very typical for an electret. With a large coupling capacitor, the electret would provide way too much low end. It kind of defeats the desired preemphasis rise and peak we want for the male voice at 2000 hertz. So a smaller capacitor, a 0.047, against the approximate input impedance of the Darlington, which is around 8K, provides a nice low cut around 400 hertz. The linearly biased Darlington itself acts as the modulated variable resistance right against ground. This is based on an AC input from the electret's output. Modulation of that resistance is based on the AC input from the electret. Static current, or Class A with that Darlington, is between 25 and maybe 45 milliamps, which is very commensurate with the expected with a carbon mic. So with 2.5 to 5 volts on the collectors of the Darlington, we're really only looking at 1 to 200 milliwatts of power dissipation. Obviously, a much smaller device could have been used, but again, the TO220 power transistor was simply selected for ruggedness and availability.
Okay, I've certainly been putting this off for a while. Let's get down to it. First, take your T17 microphone. You're going to remove these 4 screws and carefully take the front off. There were several companies that made these microphones, maybe 25, who knows. But every one of them is a little bit different to take apart, but they all should come apart with a flathead screwdriver from the front. So let's get this one apart. This particular microphone has a nice little windscreen in there on the front, little membrane. And notice that it's got an element that's very similar to a telephone type carbon microphone. No wonder it's so sensitive. I like this construction. Not all of them are going to be like this. Some of them will use small button modules, and they won't have the nice big aperture that this one has with all the big holes. In any case, you're going to be mounting the electret as far forward as possible. In this case, it would be to the center, so you can actually block the other ones from the back and only use the center hole with the electret. So as you can see on the front of the electret replacement microphone, we have the element that's gooped in, and this is just black RTV around the element, covering all those holes. So we're just using one hole in the middle, even though there's a million holes drilled in the microphone. We've sealed them all, except for one in the middle for the electret element itself. Inside the microphone, just floating in there, it's a 1 inch by about 3/4 inch board. Got the transistor. You'll see a very small trim pot there. That's the gain control. That's in the emitter of the Darlington. It's pretty much full tilt on this one, so I think you could just use the 4.7 or resistor in the emitter and you'd be okay, but I did put a gain adjust potentiometer in the emitter. This has been working probably for the better part of 25 years with no issues. This is a 2-conductor shielded cable from the microphone up to the amplifier and then down the cord to ring and sleeve. So that's it. That is the carbon mic replacement circuit. So let's take a little closer look at the components and the build. These are typical ATX power supplies from the 90s and early 2000s. These have been discarded long ago. Basically, these were the Pentium computer power supplies, and they're only between 200 and 400 watts. So they're really not useful anymore. So the landfills are full of them. Maybe your closet is full of them. There's some great parts on these power supplies. Let's see if we can find some transistors on these supplies to make the Darlington. In other words, it might be every single part we need for this project is on one of these power supplies. So let's see if we can get everything from just one of these supplies. I was able to remove parts from the boards, and it was not easy, my friends. But what I got were some transistors. The larger transistor is a 13009. It's a high voltage NPN transistor. Not exactly what we want. The current gain's not a high rating on that. But a 2SC945 transistor is cascaded onto it. The 2SC945 is a high gain NPN signal transistor. Very common all around the world. Look at those little 1/8 watt resistors. I was able to find all of them. The 470 is going to be two 1Ks in parallel. The large guy is a 4.7 ohm resistor. Perfect. I found the exact value. For the coupling cap, I'm looking for a 0.05 or a 0.1, but I got a 0.01. So if that is not adequate, I will use a 1 microfarad that I found on the boards. And also the 472 is going to take the place of the 1000 picofarad filter cap on the microphone. So we'll see if that doesn't destroy the high end. And the larger capacitor is a, let's see what that thing is. What is it? Oh, it's a 220 at 25 volts. Now, there's nowhere near 25 volts on the circuit at that point. Usually it's less than 5 volts, in fact, so that should work fine. So these are all the parts. The only thing I don't have is a trimmer. They did have 1K trimmers on the board. That would work as a gain control. We're going to put the 4.7 in and see what it does wide open. Not the prettiest thing in the world, but these are the transistors off the ATX power supply. The high voltage transistor and the BC345 hooked up as a Darlington. Plenty sensitive. I almost like it better than the other one. Try to get my mouth up here. 1, 2, 3, 4, 5. Hello, check. Oh, yeah. That looks good on the GRC9. Good modulation on the junk transistors. The next one I'm going to put on is the actual 120. Let's see if the TIP 120 works as well as these floor sweepings do. Okay, generic or not, this is the 120. 1, 2, 1, 2. This is the tip 120 that I got from Amazon. One of those 3 for $5 type deals. But it's working just fine. I have that little 100 ohm pot in the emitter just as a gain control. You might want to put that in there. But generally, most people just run it with the 4.7 or 5.6 ohm in the emitter, and that works okay. 1, 2, 1, 2. Yeah, it's good modulation. A 3-wire electret or a 2-wire electret can be used. This is a 2-wire electret, a modern one. And we've got the simple circuit that involves a TIP 120 transistor, a few resistors and capacitors. 1, 2, 3, 4. Testing 1, 2. Hello, 1, 2. Testing 1, 2, 3, 4, 5. Hello, test. Hello, test. And now let's compare that to a regular carbon microphone. This is a good carbon microphone. It works very well. T17 carbon mic. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is the regular carbon microphone. 1, 2. One, 2, 3, 4, 5. 5, 4, 3, 2, 1. This is the carbon mic replacement circuit. A little bit more feedback, of course, but it's not in a case, so that makes a difference. But we have good modulation with the carbon mic replacement with the TIP 120 transistor.